Hello and welcome. In this Max tutorial, we will create a wavetable synth from image data. New tutorial. What are we doing? We're going to build a wavetable synthesizer that is converting image data into audio. To do this, we will use jit.bfg to extract a single pixel slice from a jitter matrix and write the result into a buffer. In Gen tilde, we will then use a phasor to read from that buffer and produce the sound. We will then also implement a double buffering technique that updates the waveform only when the phasor wraps around, which eliminates clicks. We will have 3 parts. In the first one, we will do the matrix to buffer conversion. In the second one, we will play the waveform. And in the third one, we will implement the double buffering. Okay, then let's get started. I will start by creating a jit.bfg. We need one plane, float 32, and let's say, dimension 1000 by 1000, and as our initial basis, let's take noise simplex. Then I will create a jit.p window so we can see what's coming out of this one. So in order to drive this thing or get something out of it, we need to send a message. So we can do that with the pack object. I want to specifically change the scale of the output. So in order to do this, we need 2 floats. And then we also need to, so for every message we're sending, we also need to bang the output. So we can create a trigger bang list object. So first we're sending it the message and then we're banging it to see an output. Yeah. Then next thing I want to do is, oh, I forgot something here. 2. Then next thing I want to do is I want to normalize this. Wait, we don't actually need this one here. Sorry, so we'll normalize this so the output will be in a range between 0 and 1. Then it looks like this. And now I want to only take a slice of this. So now this is 1000 pixels by 1000 pixels. But I want to take slices that are 1000 pixels on the x-axis, but just 1 pixel on the y-axis. In order to do this, we can use jit submatrix. One plane, and the dimensions of this one will be, as I said, 1000 for x and 1 for y. Then I can copy this thing here, and if I'm changing anything here, you can see that we're only getting 1 slice. I will make this a bit bigger, and maybe also make this a square. Oh, that's not what I wanted, sorry. Oh. Also make this a square. Okay, now I want to be able to take different slices out of this one. So to do this, I will use a just a slider. Then I will change the range of the slider to be 1000 starting at 0. Then I will get rid of the background color by setting the opacity to 0, and I will change the on color to red. And then also change the thickness to something like 10. Here the knob shape also needs to change. So we need indicator instead of indicator plus. And the orientation will be vertical. Then with a message box, we can check the output of this. So 0 to 999, that's exactly what we want. And then I will, yeah, maybe 20 is better. And then I will try to fit this exactly on top of this P window. No, almost there. And then we can use the output of this one to change the slice we want to get here. So how will I do this? First, we need to bang the matrix again, but I guess I can just bang this BFG. So I will create a trigger bang integer. Then with a message for the offset. So X needs to be 0. We only care about the Y offset. So first we change the offset here, and then we again bang this BFG up here. And then I can patch this in here. Do something like this. Maybe make a little space. So let's see if this makes sense. Okay, now the y-axis seems to be flipped, because if you look up here, we have a dark spot on the right on top and a dark spot on the left at the bottom. But if I'm at the bottom, I can see the dark spot here, and here dark spot is on this side. So in order to flip this, we can use this object to invert the input. Now it should be fine. Okay, we're on the right now with the dark spot, and we're on the left now with the dark spot. Okay. Then now that we got this slice, we can then put it into a buffer. So first I will create the buffer. Let's call this one just waveform. This needs to have 1,000 samples, because here we also have 1,000 pixels on the x-axis. And then I will also use the waveform object, so we can look inside the buffer. Then to initialize this, we can give it the message set and then the name of the buffer. So set waveform. And then we can use the jit buffer object, also referring to our buffer we just created. We put this here. I'm input matrix too wide. Oh, because I didn't spell it right. Waveform. Okay, now it seems to be working. So the problem I'm having here is that first of all, the range is only between 0 and 1. So we need to change that. And also now it starts somewhere that isn't 0 and it ends somewhere that isn't 0. And this will introduce discontinuities into our waveform. So I want the waveform to start at 0, then go crazy here, and then to end at 0. To implement this, I will create a jit.gen that will deal with the matrix before it is turned into a buffer. So let's call this one scale maybe. Then I will put it after the normalization step. So the first thing I want to do now is the fade in and the fade out. So in order to create this fade in, we can use signed normalized coordinates that range from, -1 to 1 on the x-axis. So if we're just taking a look at this, I will create another bang object here, so I can bang this one here. We now go from -1 to 1. If I then take the absolute value of this, this will just be 1 to 0 to 1. Then I want to invert it because I want to start at 0, then go to 1, then go back. So to invert it, we can use this. Now we have this at the edges, and you can also see how this looks in our buffer. But I don't want this like linear fade in and fade out, so we can use an exponential one. And this can be done with the power operator, so using an exponent that is smaller than 1. And then you can see this is getting smoother. We can even go a bit more extreme with this. Yeah. Okay, so this is the fade in and the fade out part. And now I want to scale the input that ranges now from 0 to 1 to be in the range of -1 to 1. So I can just use the mix operator. This is essentially taking an input and scaling it to those two values. And if we just take the input waveform or the input matrix and multiply it by our fade, yeah, that's essentially what we want. So if I change this here, you can see that we're always starting at 0, always ending at 0, and the range is between -1 and 1. Okay, perfect. I think that's it for part 1. Now in part 2, we want to actually play this waveform. In order to do this, I will create a gen tilde. Let's call this one, I don't know, play wavetable. And I want to use a phasor on the outside that will drive this. And in order to control the phasor, I think I will use a K slider, and then, so this gives us MIDI notes. So the phasor takes frequency input. So in order to turn this into frequency, we can use the MIDI to frequency object and put it into the phasor. Okay. Oh, I made a mistake here. This is the title. Okay, then looking into our gen. Can get rid of this now. Okay, what do I need? First, I need to refer to the buffer. So buffer waveform. And then I need to peek into the buffer. So peek waveform at index phase. So this essentially tells us that the lookup should be normalized between 0 and 1. And we don't want to input the actual sample indices. And I also want to interpolate between the values. So interpolation cosine. Then we can plug this in here, this one in here. And what we can also do is create this a second time for a second outlet and drive this with a phasor that has just a frequency of 1 Hertz. So we can monitor the waveform. So if I'm then using a live.scope, I can see the waveform we created coming out of here. Okay, now let's take a quick listen. I will create an easy DAC, a live gain object with 1 channel and horizontal orientation. Okay. Okay, this seems to be working. And the more you zoom in here, or the more you change the scale, the more complex the waveform gets and the more overtones we will introduce. Maybe this sounds better if we make it 2 octaves lower. Or maybe just 1. And now we can also scroll through our waveform using our slider here. And I don't know if you can pick this up, but if I'm scrolling through this one, a lot of pops and clicks are introduced. And we will use the last part of this tutorial to get rid of them. So the problem with scrolling through this one here is that the buffer gets updated continuously. And you can imagine if I'm reading the buffer from, okay, I can't do anything here. If I'm reading the buffer from here until here, and when I'm in the middle of the buffer, I'm changing the waveform, then I'm introducing discontinuities. So the waveform is jumping, resulting in clicks. So in order to avoid this, we can create a second buffer that only updates when we're at the end of our phasor. So this phasor is very fast at the moment. But if we say 1 Hertz or even slower. So when the phasor is here at the minimum, we're at the beginning of the wave, and when we're at the maximum, we're at the end of the wave. So I only want this waveform or this wavetable to update when we're at the end of reading the last one. So in order to implement that, I will First of all, we need to know when the wave is starting over. So we can do this using the delta object. So this checks the difference between two consecutive values. And the difference, so if we're looking at this, the difference is usually very small, but then when the wave is starting over, we're jumping from 1 to 0 in an instance. So we have a very high negative delta. So we can essentially just say if this delta is smaller than 0, we know that we just had this jump. And we can also test this. So now you can see we get a 1 sample spike every time this thing wraps around. So this is exactly what we need. Now we can implement this double buffer setup. In order to do that, I will use a data object, which is essentially like a buffer, but just inside of Gen, so you can't access it from the outside, but we don't need that anyways. So maybe let's call this one wave. Let's just call it wave. Then we need to tell it how many samples it has, and of course it needs the same amount of samples as our original waveform. So now in order to fill it, I will use a code box. In this code box, we can call our input 1 just wrap, because this means that the phasor is wrapping around. So this is input 1. And then I want to check if we're wrapping around. And remember, this will be only true for one specific sample. So this is a 1 sample spike. And then we can check this. So we're saying if we just wrapped around, I want to copy the contents of this buffer, the waveform buffer, into this data buffer. And we can do, we can do this by using a for loop. So for I equals 0 and I is smaller than the dimension of our waveform buffer, which essentially means we're going from 0 to the end of the buffer, incrementing by 1. And then I want to get every sample. So let's just call this one value. We can use the peak operator to get the samples by their index. So peak, we're peaking into the waveform at position I. And then we're poking. So we're taking this value and we're putting it into the wave buffer. So poke, specify the buffer or the data object in this case. Then we want to use, or we want to input this value here at index I. And then we can input this here. And nothing changed because I forgot one crucial thing. We're still reading from the waveform buffer and not from the wave. So now you can hopefully hear that we don't have any clicks anymore. And I guess we could stop the tutorial at this point, but one crucial thing is, if you want to get better performance out of this, so now we're doing this copying every time this the input phasor wraps around. So if the input phasor has something like, I don't know, 1000 hertz, this will be done 1,000 times per second. So what we could do instead is we could compare the waveform buffer and the wave buffer and see if there's a difference between them. And only if there's a difference, we want to copy the waveform into the wave buffer. In order to do this, first I will create a history object. Call this one, I don't know, waveform changed. Initialize this with 0. So this means that we have a variable that is not evaluated for every sample, but that is just stored. It's like a single value buffer. Then we can perform the check. So what I want to do now is compare all the values that are in here with all the values that are in here. And if there is a difference, we will break this loop and move on. So again, for I guess I can just copy this here. Yeah, I think I can also copy this. So we have this value. This is the value that's in the waveform. And then we have, let's call this maybe previous value. This is the value that's in our wave. And then we're comparing them. So if they are not the same, so if value is different from previous value, okay, I'm running out of space here. So if they differ, what do we want to do first? We want to say, okay, the waveform changed. So this will be set to 1. And we also want to break this loop. But yeah, in terms of efficiency, this is probably not much better because again, for every sample, we have to look through this one. So what we could do instead is we could just say, okay, we're just comparing 10 values out of both of the buffers. And we can create a new index and say, okay, this is the dimension of our waveform. So in this case, 1,000 divided by the number of values we're looking into. Multiplied by I. So this means that for every sample, we will only check 10 values. And in this case, so this is 1,000 divided by 10. So first, then times 0. So first we will check at index 0, then at index 100, 200, 300, 400, and so on. And if, for every sample, we will check these 10 values. And if there's a difference between them, we know that the waveform changed and we will stop this. And now we also have to include this in here. So we can say if we have wrapped and if the waveform changed, we can do this. And this value will essentially stay at 1. So when the waveforms differ, this will be at 1 for all of the samples that the waveform differs, and this will only be true for one sample. And so we will copy this only for the first wraparound when something changed. And the crucial thing we also need to do here is we have to reset this thing. Because otherwise this will always be 1. Okay. Yeah, I think that's all I wanted to do in this tutorial. I mean, you have to be careful. If you do something like this, you will introduce a lot of overtones, which will lead to aliasing. But I think if we're playing low notes in this kind of a situation, we kind of should be safe from aliasing. If you run into aliasing doing this, you could maybe use a poly object to do some oversampling. But yeah, for the low notes I'm playing here, it shouldn't make a difference. And next steps you could implement is turning this into a real synthesizer. So also creating an envelope. You could also create an envelope for this scale here. So this could also change on every key you're pressing. Or, okay, one last thing I will also implement before stopping this is an LFO to drive this thing here. So we can use a snapshot, then a cycle. I only want the absolute value of this. So now this ranges from -1 to 1, but with using the absolute value, it would be just between 0 and 1. Then we can multiply this by the number of pixels or steps we have in here. And now we have our LFO. Maybe let's make this a bit slower. Of course, we can also try different basis functions. Okay. I think that's really it for now. Okay. I hope you got something out of this, and thank you for watching.